All right, good evening. Hopefully this works for everyone tonight. Had some weird issues the last couple weeks, but we will, our last couple classes, but we'll get going on this. So welcome to class 6. Hopefully everyone had gotten a chance to get caught up over the weekend, and we can now move forward with a little bit more fun for the technical folks here tonight. Again, just a reminder, the housekeeping, just keep the chat relevant to the topic. Just, we're all adults, just act like adults. I appreciate that. Okay, so so far so good. First 4 chapters are done. I would say I agree with that second bullet point. That was the hardest part, and we're past it, right? We got through those security models and encryption. We're ready to go. So I think, as the note says, maybe 160 was a little ambitious. So we're going to be humming along, but quite a few fewer slides tonight. Also, a lot more fun for me because we're talking network and technical controls, which is where I think a lot of us came up with or from. Make sure we got good audio. Let's see. A little quiet. All right, let me just give me 1 second here. I want to make sure I turn this up a little bit. All right, I'm going to just check that here as we go through the quizzes and make sure that we're not having any issues with the sound. All right, so get back here. What type of sprinkler system would be best for a data center? So we talked through this in the last class and what the differences were. Wet pipe meaning water to it. Dry pipe, there's no water in the pipe itself, pushed by air. Deluge, which is going to drop water, and pre-action, requiring two different things. So pre-action, it would be the best. In a data center, art gallery, any of those types of things where you have sensitive information or sensitive, electronics, books, art, things like that. All right. What is the primary drawback in using dogs as a perimeter control? Training, yeah, okay, that would be a drawback. Cost is a drawback. Appearance could be a drawback. It's liability in this case, right? If a dog bites someone, you could get sued. This is a good example of which is the most correct. Liability is the most correct answer. Okay. RSA algorithm is based on which one-way function? Here's where that memorization just comes into play. You just have to know, oh, okay, RSA, that is factoring composites into their primes. You just memorize that. Remember, we were talking about, hey, I get it, there's a lot on here. You just have to memorize and know and say, what are these triggers? This is a great example of just knowing what the trigger is. All right. Here's a good example. What I want to look at here when we're taking the exam itself, when you see a big block of text like this, read the question first, right? Then go back and understand what they're looking for. So in this case, what security feature allows this? Okay, so we know we're looking for a feature. So we're surfing the web via wireless. Your wireless becomes unreliable. You're going to plug into a wired network to continue. When you change physical networks, your browser requires no change. What feature allows this? Layering, right? It's not abstraction. It's not the hardware segmentation. We're not isolating processes. We're working with layering in that case. All right, same thing here. Big blocks of text. Skip down to the question. Understand what they're looking for. All right, what type of attack has been launched? All right, so criminal deduces that an organization is holding an offsite meeting and has few people in the building based on the low traffic volume to and from the parking lot. Uses this opportunity to break into the building to steal laptops. All right, well, aggregation is collecting parts of maybe not sensitive information and getting sensitive information from those parts. So that's probably not it. Emanations, no, that's where it's going to be looking at like lights and things like that. A maintenance hook, no, that's from a developer. That's where they put it in to be able to do maintenance, then forget to take it out. it's inference. We're going to take unalike data or information and put it together to understand what's going on. We don't necessarily know for sure that they're having an offsite, but we're saying in this example, there's very few people, there's low traffic volume, uh, there's obviously something going on. They're not there. It's outside of the norm. So we're inferring that attack. All right. What is the most important goal of a fire suppression system? This is about the easiest gimme you're going to get on the exam. Let's see, hang on. All right. What is this? So, sorry, I saw in the chat come through, so we're good. What is the most important? Gimme. Anytime you see any of these things and you see in the answers the safety of personnel or human life, something like that, that is your answer right away. Obviously, the rest are important, but it's not the most important. Human life will always trump everything else. All right, easy. Now we're going to be going through Domain 4, Communication Network Security, so designing, protecting networks. We're going to cover the architecture design, network devices, protocols, secure communications. This is easy for techies, right? If you've been doing network management, systems admin type work, a lot of this is going to just click with you. It's things you do day in, day out. I know for me personally, this was probably the easiest chapter, just because, again, our domain, because that's what I did. If you're not a techie, it may be a little bit more challenging. This is more where you're going to have that memorization versus what some of those IT folks with that IT background will be going through. All right. So we're going to talk through network defense in depth. What we have to assume is that the attacker has already compromised your perimeter. So what do you have that if they get in, they have multiple layers they have to get through? This will be network segmentation, the isolation of critical or sensitive devices, networks, things like that. The NSA has that really great methodology for adversary obstruction. Again, like it says, it's not testable, but I mean, honestly, it's a really interesting read. And that is what it looks like. So what is network defense in depth? Well, this is a good example of that, right? We're going to start at the outside, right? Advanced threat. So that's your, as it says, FireEye, Cisco, Ironport. It could be, your outside firewall working your way in. So then once they get past that, well, now they have to get through your intrusion detection, intrusion prevention. All right, well, if they get through that, we have web security, web filtering for the end users, and email, and forensic, and data loss. And so you can see how these things build. And one of the things you'll notice on that example is it's not all the exact same solutions in there, right? We don't want to trust all of our defense in depth to a single provider. Reason being, if that provider has that compromise or has a 0-day they're not detecting, then none of your levels are all as secure. All right, these are these fundamental concepts: simplex, half duplex, full duplex. Simplex, one way. You're listening or you're broadcasting. That's it. Car radio, listening to the music. Half duplex is your walkie-talkie. So one sends, receives, the other sends. Right? You can't do it at the same time. And then full duplex, that's going both directions. That's that face-to-face conversation. If you can remember those three concepts, you'll be in good shape. Baseband broadband. So baseband, one channel. We only have one signal. Broadband, well, that's your cable TV, right? Multiple signals coming over. Realistically, that's about all you need to know. Baseband is going to be your Ethernet. Broadband is going to be cable TV. You have multiple channels. You have one channel, one signal. It's I think it's pretty straightforward on that. So keep going. We need to know analog and digital. Analog, that's that continuous wave versus the bits, ones and zeros. Right? So analog would be the old telephone systems versus a digital voice over IP. All right, you will need to know the difference in these different area networks. So personal area network, Bluetooth, right? So close range. Think about like within your house type of a thing. So however far Bluetooth could go. A LAN, local area network, think of this as a building or a network segment, right? A business unit. So keeping it fairly small. I always just said it's a building. It's just the easiest way. The metropolitan area network, well, that's going to be your campus. That's how I always remembered it. City campus, um, uh, colleges, hospitals, right? Those are going to be typically more metropolitan area networks. A LAN would be a building within that MAN. WAN, wide area, so this is going to be across states or cities, um, across the country. So if you have offices in, Minneapolis and in Denver, that would be your WAN. And then global is your collection of your WANs. So global starts big, collection of WANs, collection of MANs, collection of LANs. PANs are going to be personal. Again, like I said, if you've done IT tech work, this is probably really going to be, right up your wheelhouse. All right, so circuit switching, we need to know this. What they're going to do is when you do the call, this is that old phone system. That diagram really does a good job of showing it. When that connection or when that comes through, there's a physical connection. Once that is connected through that for that purpose, it's dedicated. Nothing else can use that path. Dedicated bandwidth for point-to-point connections. Again, I think the circuit switching, the one you want to think of it is the original voice, right? You had the old operators that would plug in and make that connection. Okay, so packet switching network. So instead of using that dedicated circuit, right, we got a physical connection and everything goes over it. We're taking that data and breaking it down into packets, and we're going to talk about some of that stuff as well. But it doesn't matter if there's how many routes available. It's going to choose what is the right one, and these are going to be those devices and network devices. They're going to send and say, here's the fastest way. So those packets don't always follow sequentially, right? So if it's missing, they're getting out of order, right? Because they took different paths, they put it back together. So a good graphic for that kind of shows this. So, each of those little devices that we're going to consider that a router, right? So packet 1 goes up to the top and around, packet 2 goes down. Doesn't really matter what order they're received by that end device. They're all numbered and they'll be put into the right order when they're received. If there's something missing, they'll send back a request and it can get resent. This is more what you would see today in networks. All right, we're spending a little time on the OSI and the TCP/IP model. So we're going to have to know those. Doesn't have to go, we're not going to go super in depth on these, but you absolutely need to know at what level do different things play at. And then how do those two models map together? So as you can see, it's, there's layers. Probably everyone knows, well, most people know there's 7. We'll go through all those. And whatever happens at one layer does not directly affect another layer. So again, that's that if we're going from wired to wireless, it doesn't matter to the web browser. All right. So that model, it's how the network protocol works. That's really what it's saying. Here's how we do this. Protocol is the set of rules that they use to communicate, right? So when I use TCP/IP or UDP or whatever, we're going to talk about TCP/IP for the OSI. But whatever that model is, that protocol is, the endpoints know that, so they know how to communicate with each other. All right. So OSI, we use reference point. So layer 1 is physical. So we all talk the same language, right? We all know we're going whatever the direction is. It is abstract, right? It's not like this is exactly how it is, right? It's more of the how it operates. And then, so it was developed by the ISO and the X200. I don't think that that's testable. I mean, it probably doesn't hurt to know, but I don't believe that was testable. All right. So this is the OSI model. Right? So we're going to go through all of these in more detail. I don't want to spend a lot of time on this. This is a good slide to study because it does have everything in one place with kind of what a high level what these things do, what you'll need to know from a testing perspective. As we got a couple other really good study slides in here as well. Of course, the easiest way to do this is through mnemonics. These are some, pretty common ones. Please do not take salespeople's advice. That makes me laugh. I enjoy that one. But there's, probably a dozen of them out there that I've seen, that whatever works best for you to remember the order, use that. All right. So the physical layer. This is the actual medium, right? So think of this as your cable, your NIC card. What is, or not? I'm sorry, the cabling, the connection, right? When we look at this for the exam, this is very important to understand. For the exam, layer 1 is hubs and repeaters. Does not matter what, especially as we get to switches and where they fall into this. That doesn't matter what the real world or manufacturers say. For the exam, know that if you see a hub or repeater, it's working at layer 1, at the physical layer. So what is the data being carried across, right? The light, so fiber optics, electricity, electricity, radio waves, whatever it is, and then if it's copper or fiber optics. So we need to know that. You'll need to know those cabling standards, and we'll go through some of those a little bit, but and there's a good little cheat sheet to kind of remember some of that stuff. All right, so physical, it's your binary transmission, right? It's those wires, it's the connectors, whatever those physical pieces of that connection are. All right, so data link. One of the important things on data link is that last bullet point there. It is divided into 2 sublayers. Right? This one goes between both the physical and the network. Right? It kind of communicates. We need to know that 2 sublayers. If you see this on the exam, which one has 2 sublayers? It's data link. So you need to know media access and logical link. Right? So this is going to be taking that connection from the physical cable through your Ethernet card, and then moving it to your up to your network level, the next one up. For this here, layer 2 for the exam, and regardless of if there's layer 3 switches, it does not matter for the purposes of the exam. Okay, if you see layer 2, switches and bridges are layer 2. Period. It is what it is. Just make sure you understand that. All right. So data link goes between layer 1 and 3, touches both of those layers. That's an important thing to remember. Okay. Media access going from physical to layer 2, and then logical link going from layer 2 to layer 3. And then switches and bridges are considered layer 2 devices. All right. So what is that doing? As it says there, it's that reliable transfer of data across the different media. So it's taking it from that physical into the network layer. So MAC addresses, things like that, are handled there. All right, networking. How do we move data from one system to another? So IP, v4, v6, those all live at that networking layer. So Again, for the exam, routers, layer 3. Just, I don't know, it doesn't matter what anybody else says for the exam, that is the correct answer. Okay. So connectivity and path selection, right? Remember we talked, this is where routing lives, packet switching. This is where we're going to see what is that best path lives at the network layer. All right, transport layer. So this is where it's going to make sure that you got the packet sequencing, error detection, all those things are put into place. TCP, UDP are layer 4, resending, resequencing. You know, when we look at that, this is where it's recompiling, right? We talked about just a minute ago, we have packet switching, they may come in the wrong order, there may be packets missing. Layer 4 puts all that stuff back together and yeah, like it says, handles that end-to-end communication. So between hosts on a network, this is where that communication takes place. Right? This is where we have that fault detection, recovery, that reliability, all that stuff really comes into play in the transport layer. All right, session layer 5. So RPCs, right? So this is that connection between the applications, right? So how do we connect? Once we've got that connection in place, for that, this is now where your client and server connectivity and communication takes place. So this could be, depending on what is being used, simplex, half duplex, full duplex, all three of those are valid for layer 5. So sessions between applications, that's really what you need to understand, right? So after we've got a connection, that network connection is going and good, and we're going to now use this to manage that client server. It's probably the easiest way to remember that. Presentation layer. I think when you see this, it's presentation, it's presenting, right? This is what you would see as the user. So think of this as your GIF, JPEGs, TIFFs. What are we going to see? Presentation, presenting. It's taking all those bits of data and making it viewable for either the application or for the user to digest. Format of data structures. What is it looking for how that data is coming across as it comes across that application layer. And then application, this is where you're actually interfacing. So this would be the actual application on your computer. Whatever that is, like it says there, your web browsers, your Word, Excel, instant messaging. It's where you as a human are interacting with the computer application using what is being presented at that presentation layer. So, and then you will need to know protocols that are on there, Telnet, FTP. Those are important to understand and run at that layer. Yeah, there you go. So network processing, just how do you interact? Email, file transfer, terminal emulation, all those things where you're actually interacting with the device that resides at the application layer. All right. There's some mnemonics around that. Just whatever one works the best for you, go ahead and use. And then this is the other slide I think is a really good one to use to memorize. It gives your layers here, and then kind of what at a high level in the far left there under that layer, what it is and what it does, and then a good example of what they are, and then what what protocols and things work at those layers. You'll see the DoD4 model there. It's very similar to the TCPIP. The naming is just a little bit different, but this is a great resource. What you see on here is kind of what you'll need to know for the exam. All right, TCPIP model. So created by the Department of by DARPA in the 70s. So it's going to be using the suite of protocols to work on this. So yeah, I'm just going to bring up the next slide here. It'll be easier to explain. So what you'll see is you actually are going to now be breaking down and they combine the physical data link into a network access layer. And you will need to know how these map because they will give you examples using data link or physical descriptors and then give you a network access layer, right? So you'll need to know how these map. Everything you see in physical data link does map over to your network access. Network layer is now called your internet layer. Transport is the same. And then the top three all get combined into the application layer. So not a lot different in terms of what works where. It's just that they've grouped it differently. So this just talks about it, right? So layer 1 is now combining the layer 1 and 2 of the OSI model. And then, so now think of that, it's now taking all that physical devices and then the NIC cards into one, right? It's all combining that into just one layer. So now you're looking at your networking as your internet LAN and WAN in that layer. Just something to remember. The way I did it, quite frankly, is I just memorized what the differences were, and I was familiar with OSI, right? So I just knew if I saw a network access, it meant it was either 1 or 2, right? Or if I saw something that was presentation layer, okay, that was going to be application layer. I don't think there's enough outside differences to really take a lot of time. And as I mentioned here, you do have a really close mapping. The names are a little different, but use this to kind of understand and as a study reference. All right. So the internet layer aligning with layer 3. Right, this is where your I protocols, right, IPv4, v6, ICMP, these all go through the internet layer or the network layer, the OSI model. Best path and packet switching, same thing, right? Just make sure you understand the difference in that naming convention. Host-to-host or transport port layer. I think I've only seen it as transport, but you could see it as host-to-host. This is where your internet to the application, right? Applications are on two networks via ports, TCP, UDP under the transport layer. So TCP, we want to know that is connection oriented, right? So what you're seeing here, I could read through them. That would be, whatever. These are the things you really need to know about this, and we're going to go into a little bit more. But what you see on here, you don't need to go a whole lot deeper than this, and then what we'll see on some further slides, because what you'll see is what is the protocol that provides reliable full duplex transmission and allows for retransmission, right? So we need to know, TCP is connection oriented, right? One way from source and destination. We're going to package that application. We're going to break it up into those different packets and send it across, right? Reliable, flow control, right? Acknowledgement, windowing, all those things. So what you see on here, this is what you'll need to know. And again, we'll go through a little bit more on some of these protocols a little later. Saying here, UDP, right? Connectionless protocol. We need to know that. Okay. So what you'll see a lot of times, UDP is going to be faster than TCP, right? Because it doesn't care if you got it or not. TCP is going to check and make sure, hey, is it here? No, I'm missing a packet, resend. UDP is just going to send, right? So you'll see UDP used for like streaming services where, if you lose some packets, you're probably never going to notice that because it's faster. It is unreliable, right? The joke on this one is I was going to tell you a joke about UDP, but I couldn't guarantee you'd get it. There you go. There's your joke of the day. But that's kind of the big difference between TCP and UDP. TCP, I want to make sure it's there. It's a connection oriented. I'm going to make sure I actually acknowledge that I got your transmission. If anything isn't there, I'm going to request it and have it resend. UDP, that's going to be faster. It's just going to send those packets. If you get them, you get them. If you don't, you don't, right? It's got that error processing, retransmission, anything if it's going to be included is handled by something else. It's not going to be handled by UDP. All right. Right, there it goes. All right, application layer. So for the OSI is going to be layers 5. I'm sorry, TCPI application layers combining 5 through 7 of the OSI model. Right, so it just really just says, hey, all these things that are kind of user focused, we're just going to put it into the application layer. So client server type of things, think of that. And then you can use TCP or UDP as your transport layer protocol. Just memorize on this that SSH, Telnet, FTP. Again, going back to that diagram on that earlier slide, that's a really good study guide. So application is your process layer. This is where your high-level protocols are. So those are you'll want to know, right? If you see HTTP, SMTP, FTP, any of those protocols on there, this is application. This is the highest one. And the way that I like to think of this is when, how do you know what application runs there or protocols run there? If you're going to interact with it, then that's on that application, right? And then data is properly packaged. So here's a kind of a cheat sheet here of kind of what that looks like, what layer the different packets are at. You don't necessarily need to know everything in here, right? Know the well-known ones. When you look up here at, application, FTP, Telnet, SMTP, IMAP, maybe R shell, TFTP, HTTPS, make sure you understand these big, well-known Texas Plus. We'll go through that. That's really what you need to know. You're not going to necessarily need to know, XOT or ISO-DE, some of these lesser known kind of branches off. Just know transport is TCP and UDP, right? Hopefully that makes sense. Again, really good resource right here to understand kind of what's at what level, just so you get it. All right, encapsulation. What we're going to do is we're taking information as it's kind of split down, right? Because we got packet sizes, and we'll go through all that. But it's going to add headers to it so that I now say, all right, I've got this big chunk of data. I'm going to break it up, but I'm going to add a header so that I know how to put it back together, right? So as it goes up or down the stack, it's going to add headers to it, or it's going to take them away as it goes. So if I'm going to bring it up from a 1 to a 7, it is going to be layered and then go the other way, right? So you got, right, oh, here it is. The data moves down the stack. It's going to be going from 4, it's going to have that, and then it's going to be added a level 3 header, then a level 2, then a level 1, and then as it's received on the other end, the opposite happens. So, here's kind of that example of that. So you've got your data streams at the top on those top 3 layers. Then transport layer breaks that into the 3 segment sizes, the packet sizes that are agreed to based on the protocol. The network layer is going to add your network header, right, to each of those segments or to each of those packets. And then when it goes down to the data link, you get your frame header, trailer, so that when it's received, we know it's good. Physical turns it into 1s and 0s. On the opposite end, it's going to go through the opposite status, right? So destination receives it. Physical is going to turn it from 1s to 0s to the frame header, network header, data, frame trailer, and then on up the stack. So here's a good example for email, right? At the high level, the user creates that email message. Here's your data segmented into the different packets. You're now getting your network header added to the data chunks, added your frame headers because of your network layer, and then into the bits down into the cloud and across the network. So when you see encapsulation, that's what that means, right? We're going to take it and add headers at each level on the sending side, and then on the opposite end, it's going to take and remove those headers as it moves up the stack. All right. All right, so TCP/IP, kind of talked about it at very high level before. Again, it's kind of really the amount of data and the amount of depth you'll really need to go to, right? So TCP/IP is the protocol suite, so it's got TCP and IP at those two layers, right? So you'll need to remember IP is at 3, TCP or UDP is at layer 4. Then it has all kinds of things on top of that, right? So 5 through 7, go back and just make sure you understand the protocols, right? Where do those different protocols live? Telnet, FTP, SSH, where do they live? Kind of the high level ones, right? IP is always going to be an internet, right? That's going to be great. That's easy to remember. But then you have ARP, which goes across, right? So ARP is going to be looking up those MAC addresses. It's going to go from network access to internet, right? So you'll need to know kind of at a high level, again, the well-known ones. Don't worry about the truly obscure ones. All right, MAC address, it's the hardware address. That's it. Burned in at the factory, you can tell what the manufacturer is, right, by the MAC address. They're given a range, right? And then they do their own custom ones at the end. But these are going to be unique, right? We have to have unique MACs on a network. You can change them in software, but they should be unique. They were 48 bits. So what you'll have is the first 24 is the organizational unique identifier. That's what you'll want to know. So like that's where you're going to know it's a Cisco, the Juniper. It's who made that NIC card, right? And then the last 24 are the serial number that identify that unique card to that manufacturer. So what that looks like is this, right? So you can do an IP config. This is in Windows. Shows you your physical address, and then that's the breakdown. So you got who made it, and then what is the specific one. And again, these need to be unique. Otherwise, you run into some issues on a network, and there's other attacks around some of those things, which we'll cover. So that's the historical, and they now have the extended for 64-bit. So now really what this allows is you still have your unique identifier. That hasn't changed. That's still 24, but instead of only having 40 bits, you now have, instead of having 24 bits for the serial number, you have 40. So same concept of going from IPv4 to IPv6. We just allow, by increasing that address space, it is increasing the amount of devices that can have a unique identifier. All right, IPv4, this is the fundamental protocol of the internet, right? So this is IP, this is what everyone still uses despite, IPv6 or the addresses being run out and all this stuff we've heard and trying to move into IPv6. It's simple. It's all it's done. It's designed to carry the data across the network. TCP handles all the error control and all that stuff. IP just is making that connection. Looking for ICMP, so you'll have, I'm sure you've heard ICMP pinging. IP, it's connectionless, unreliable, right? So it's best delivery. That's where the TCP goes on top of that. We're going to be doing the 32-bit, right, where this is at quad 4s or dotted quads or whatever you want to call it, right? So it's at 192.168.2.4. It's what most everybody is familiar with. In fact, even now, it's very rare that we see a IPv6 network in doing our assessments and scanning and things like that. So 32 bits, 2 to the 32nd, so that's 4.3 billion addresses. However, right, that isn't a whole lot when you consider all the devices that are out there. So IPv6 uses 128-bit. We'll go through that here in just a little bit. But you know, you can see 32 to 128. That's a significantly larger number there. All right. So what you'll need to understand on this slide is what are the fields and what are they doing, right? So with this, need to know IP header 20 bytes. That's it. No option, 20 bytes for an IP header. If they say on the exam the header is 20 bytes, you know it's IP and you're, you know, IPv4, you're set. That's a kind of a dead giveaway. Does have these fields in it. So again, what's the versioning? What's the length of the header? What's the type of the service? So this is where you would see some, well, here, let's go to the next slide. So here's what this looks like, right? So what the version, the header, what's your type of service? Here's the remainder of the information, and then it goes back. I think this is a little bit easier to understand, but I'm going to flip back here so you guys can see this for just a little bit longer. So what's your type of service? What is it coming across as, right? Is this kind of where QoS would live as well, or would be used based on that type of service? QoS being you know, quality or you know, kind of prioritization of that network traffic. So IP, if we're going to be using IP fragmentation, what is that? Yes, is it on or off? What's the time to live? So how long can it go before it just dies? Otherwise, if we didn't have that, it could sit out there forever, right? It's going to just keep bouncing around. We need to know after a certain number of connections, if it hasn't made its way to its destination, that's it. It dies. What protocol is being used, you know, right? So is it TCP, UDP, so that the receiver knows how to communicate with it, and then where's it coming from? Where's it going to? So going back to this, this is another really good slide. So here's your versioning, right? This is the 20 bytes for that packet, showing all your different information levels, right? Your version, your type of service, the identification. Is there any offsetting, you know, based on those IP flags? What's its time to live, right? This is where you'd see maybe 20 hops, right? If it can't get past 20, after 20 connections, it hasn't got its way or hasn't found its way, it's going away, right? I would say memorize kind of these things on the bottom here, understanding, you know, at a high level, what protocols could run as embedded in IP. Yeah, IP datagram, fragment offset. You know, I don't know if you don't need to know this information per se. You need to know there's a header checksum, right? What is making sure that it does receive it and knows that it's not corrupt. Here are your IP flags. You need to know that. This is where it's going to say, you know, nope, don't fragment this across, or hey, more stuff is coming. It's pretty much kind of at a high level, that's your IP protocol. It tells us what are we using, what type of data, what service are we going to be doing, and what's the embedded protocol. Where are we going? Where am I coming from? All right. So with fragmentation, if the packet is larger than that max transmission unit MTU, you want to probably remember that acronym. What do we do? So if we're allowing fragmentation, we're going to allow a router to take that packet and break it up into multiple different ones. So here, what is the max transmission size? Is the maximum PDU packet distribution? I can't remember what that PDU stands for. It's been a really long day. Anyway, so fragmentation is going to break that larger packet into smaller ones. So if we have a packet, typically it's 1500, right? That's a typical IP packet. If we have a packet larger than that, what we're saying is if it's larger, break it up so that you can in fact send it. All right. If we do have that flag that says don't fragment, and the router gets it and it's larger than the PDU, it's going to send it and drop it and say, nope, fragmentation is needed. I can't process that. So kind of at a high level, IP fragmentation, if we have a packet larger than the PDU size, we need to break it apart. If it has that flag that says don't fragment, the DF, well then it's gonna be dropped and sent back saying, sorry, fragmentation needed. All right, so IPv6, this is supposed to replace IPv4, right? So it's got that 128-bit addresses versus the 32. It is simpler routing, it's simpler address assignment, and there's where it says it's 340 undecillion or sextillion addresses, slightly higher than IPv4. That's what that number actually looks like. So that was why it was supposed to really be there. That was the primary driving factor to go from 32 to 128 for the IPv6. In theory, we would probably never run out of that number of unique IP addresses. All right, so the IP6 header is larger and simpler. All right, we're going to go through that here in just a second, but you can see right off the bat, hey, we've only got these 5 things. Right? What version are we using? So it's going to be 6. The traffic class and flow label, so it's kind of the same as that type of service. This is your QoS, so we know how to process and handle that, prioritize the traffic. What is the payload length? Same as the length in IPv4. What's the next embedded protocol header? And then hop limit is your kind of the same as your life, right? So this is what that looks like. A little easier to understand. When you look at IPv4, it's got that quad 4s, or dotted quads, I mean. And then this one is going to be in the segments with the colons between it. We'll show you that here in a second. Kind of interesting. I still, like I said, I think we've maybe had 1 or 2 organizations that have used this. But again, source and destination. So it's going to go through your version, right? Same exact kind of approach, right? What are we doing? What am I using, 4 or 6? How do I communicate? What's this connection going to be? Okay, 6. How am I going to prioritize it? What kind of traffic is this? Your label, your payload length, how much is coming? What type of header is coming next? So same values. This is important as your IPv4. That's the nice thing. You only have to memorize one set of protocols that could be embedded within that IP header. Your hop limit. So again, 30 hops. If it hasn't found its way home or to its destination, that's it. And then where is it coming from? Where is it going to? These are those 128-bit addresses. So, on here, as it goes through it, there are obviously some security concerns around this because they can statelessly auto-configure a unique address, right? So we don't need DHCP anymore, or we don't need static addressing. Now, is that ideal? Probably not. as a security side of it, but that's kind of as an off topic on this. So what it's doing is it takes the MAC address. Remember, that's that unique unique address, unique value, and it's going to use that to create the IPv6 address. So again, it's 128 bits. It's using colons instead of the periods. And then you can take a large number of zeros, a series of zeros, and condense it into 2 colons. This does get a little bit tricky when you start looking at it, and we'll go through that here on the next slide to make sure you understand where that is, and if you see 2 colons, what does that mean? How many sections should you be seeing, right? You're going to need to know all that stuff. DHCP can be used, may be used. If you're managing network, I would recommend it if you're going to use IPv6. But all right. So with this, on this slide, what you'll need is to understand, looking at this first section here, global and link for the scopes. Okay. So global means it's routable, it's going outside the local, and then link is within the local. You will need to know the difference if it's FCO1 or FE80, what that means. Now here you can see there's some dots, 2 dots together, there would be zeros in there. So instead of having to write out the entire full network, so here you can see what that would all look like, we can just do the 2 dots and get rid of all 4 of these, right? It just makes it a little bit shorter and easier to read as on that. So make sure you understand FCO1, global, it's routable. FE80, link local, only local network, right? Yeah. So with this, I'm on a one of those hockey stool things or wobble stools, so this is a new experience. Host using this is how it does that auto configuration, right? So here's your MAC address. Boom. It's going to embed your FFEE in the middle 2 bytes. So you'll see that FFEE. And then setting a universal bit, going in prepending that network prefix to that. So FCO1. You see this whole long address, right? That would be a lot to go through, because right here is really what I need to know. This 20C, that tells me who I'm going to. The FCO1 and all this is going to be telling me, is it link local or global? So you can see we just convert all these sets of zeros down to a single set of double colons. And you can use both IPv4 and v6 simultaneously. So, if you're not intending to use IPv6, you should probably disable it. So, yeah, security challenges. It's automatically going to configure link local. So you don't even have to do anything. And now your hosts on your network are going to be connecting and being able to communicate on IPv6. It's the risk of that. Well, if you don't know what's running, are you watching it and monitoring it for an attack, right? If you don't know it's even available, that makes it really hard to defend against. Yeah, if you're not using it, disable it. Group policy or however you want to do that. All right, so back to IPv4. Before this, we had classes. So you need to know the classes and how these break apart. You need to know, the A, B, C, D and E, D being multicast, E being reserved. That's probably about all you'll need to know for those. You will need to know their starting addresses and ending addresses. With this here, you want to make sure you understand what the network is and then the rest. So this would describe our network and then the host. So we have on a class A 128 networks with 16 million host addresses or usable addresses per network. Now we do obviously get to, we're splitting those and stuff, but this is how it started with the classful networks. And we'll go through a little bit more here in a second. So for this, remember CIDR, classless interdomain routing. So what this does is it says, instead of only being allowed, go back here, a class A, right? If I have a class A assigned to me, I have 128 networks. So if I get a class A, I got one of these maybe, with 16 million, almost 17 million hosts. That's a lot of potentially wasted space, right? So what CIDR does is it allows you to start breaking those up. So we're not so reliant on the classful networks. So if you look here, 10.0.0.0 IP addresses go starting with 10. So your network is 10, right? The first 8 bits are your network. Then the rest are your host address. Okay, so 10, this is your network for class A. If it was class B, it would be the 10.0. Class C would be the 10.0.0. Okay. Then the remainder, whatever is not your network, that is your host address. So CIDR is for class A is /8, meaning the network portion is now 8 bits long, leaving 24 for the host. Remember, 32-bit, right? This is a number of bits for your network. So if the class C, 192.0.2, right? So here is our network identifier, and then here is your actual host address. Right. So here you can see 192, so 77.253. So in this case, class C CIDR is 24, meaning the first 24 bits, right, are your network, and the remaining 8 bits are your host. Okay. Really important to understand that. It's not too difficult. I don't remember having to do a lot of subnetting in terms of figuring this out, but you'll have to understand it. All right. So now, once we have it in a CIDR, now we can do additional sizes, right? So if I only need 128 addresses instead of the full 256, right? If we're using a classful C, I have 256 points here, right? Or, well, 253, I apologize. Can't use, we'll go through that. Sorry. There's 253 hosts. So now, if I want to take if I only need 128, I can chop that and go, I'm going to take one extra spot and make that into 2/25s, right? So if I only need 64, I can go and slash that and do a /26. So again, I don't remember having to do a lot of networking or subnetting specifically on this exam, but you'll need to understand what CIDR is and how it works. So it's going to allow you to split those subnets, those classful subnets, into smaller, more usable subnets. Again, it's going to take, the slash is the number of bits in that address that are going towards the network versus the host. That's what you'll want to remember on that. Okay, RFC 1918. This is one of the RFCs you will have to memorize. Okay, as it says on here, typically you don't need to memorize a lot of RFCs. It's good, interesting for historical purposes. But this one you absolutely need to know. There's 3 blocks of IP addresses in RFC 1918 that are for internal traffic. So 10 dot, if you see anything 10.0.0.0 to 222.255, or your /8 CIDR, right, network host, everything here is private. Same with 172.16 to 172.31 and 192.168. So if you see any combination of these, you have to know that those are private, or I'm sorry, internal. Those are not internet routable. Okay. So That's really what you'll need to know on that. Just remember RC 1918 and what are the 3 blocks of internal IP ranges that are not internet routable. Network address translation. So this is kind of why we haven't seen that bigger uptake of IPv6, right? We thought we were going to run out of IPv4. Well, now what we can do is, it doesn't matter how many companies use 192.168 addressing schemes internally, because we have a way to now make all those, because they're not internet routable. So now we've increased the amount of network addresses available. So network address translation is going to translate those RC 1918 addresses into internet routable addresses. So you need to know 3 types. You will need to know the difference in these 3 as well. So static is 1-to-1. Right? If I have my IP address is 192.168.1.47, my public routable IP address would be that 192.0.2.252. It's 1-to-1, 1 internal to 1 external. Pools or dynamic, we're going to have a group, right? So I might have, 24 public IPs, and as people use them, I need this one. It goes out, you do your what internet routable activity, comes back. Once you're done, it goes back into the pool. Somebody else can use it. And then port address. So this is many to one. So this is that's really what we see a lot of now, right? So everybody in the organization looks like it's coming from a single public IP address. So you'll want to make sure you understand those 3 concepts. So that's what that again looks like. So if you have a static, it's a 1-to-1. A pool, you have those coming in and then being returned. Right. So in this case, you have the .17, 21, and .56 getting specific IPs. When they're done with whatever activity they're doing, they'll get returned. Somebody else would be assigned that. And then that port address translation is saying anybody coming from that 192.168.1, it's all going to appear it's coming from that 2.20. All right. Moving along, hopefully not too fast for people here. ARP and RARP. So ARP is address resolution, making sure you translating that layer 2 MAC address to a layer 3 IP address. So what happens is you go, hey, who is 192.168.2.140? Who are you? Who has this? The ARP reply would say, oh, this is at this MAC address. Then it knows how to where to go, how to connect. So one of these things you see is ARP poisoning attacks, where an attacker goes and they say, hey, who is 2.140, and instead of it being that accurate actual answer, they're going to put in their own MAC address so that the packets flow through them instead of going to where they belong. Reverse ARP is going the other way. Right? So this is that disk workstation saying, hey, who is this person? And the RARP server is going to go, oh, here, they're over here. Here's how you get there via IP. Right? So ARP is looking up MAC addresses. Requesting an IP. Asking, hey, who is this IP, and receiving a MAC address back. Reverse ARP is saying, hey, who is this MAC address, and receiving an IP address back. You will want to make sure you understand the ARP poisoning as well, that there are risks to that. All right, so unicast, multicast, broadcast. Pretty straightforward. Unicast is 1-to-1. I'm talking to you. Multicast, 1-to-many. I'm talking to everyone, not everyone, everyone in this group, right? And then broadcast is, I'm talking to everybody. So think of this as You know, one-to-one, you're having a personal conversation with someone. One-to-many, maybe a group conversation. One-to-all, you're out there with a megaphone just yelling to whoever is walking by. So limited broadcast and directed broadcast is sent to all stations on the LAN, right? We're just, everybody gets it. Limited is saying it's never going across a router. Directed is can be sent to other or sent from remote networks, right? It may be directed across. So just make sure when you understand broadcast traffic that there are two types. Limited doesn't get routed. Directed is routed. It goes across the router. It's directed to another network. So limited stays on its own. Directed is directed across. All right, so that layer 2 broadcast, everything in the broadcast domain. Again, switch. Remember, for the exam, a switch is layer 2. Anything connected to that switch is going to get that traffic. It's not routing it and we're saying, oh, this is comes in on this port, it's only going to this port. Switch, everything is available to everyone on that switch. Yeah, everything on that by everyone who's connected. So again, I know there's layer 3 switches and all that in the real world. Doesn't matter. For the exam, a switch is layer 2. Everybody connected, any device connected on a switch will receive traffic, broadcast traffic as it's sent out. All right. Promiscuous network access. So we're going to be accessing all our unicast. Remember, unicast 1-to-1. Well, promiscuous networks access allows us to see that, right? So network intrusion. This is where you would see, you know, if we're going to be doing maybe some troubleshooting, we'll set up a port into promiscuous mode and be able to see all the traffic. Now, yeah, NIDS or network intrusion prevention systems require that so they can see everything that's happening, right? Typically, if it's unicast, it's only 1-to-1. We can't actually see what's going on. With promiscuous mode, we're allowing it to see everything. So switches do provide that isolation, allowing it to only receive unicast traffic sent to us. Again, we can use a hub port, switch span port, or a tap for promiscuous network access. So what you want to remember about promiscuous is it's allowing you to access unicast traffic on a network segment. It's really the important part here. You know, I don't think they're going to specifically ask you what would use it, but we want to make sure we understand we can access or monitor all traffic on a network, regardless of what broadcast type. Or, I'm sorry, traffic type. All right, so TCP works with IP, right? IP is just that connection. It's not reliable. It's just going to go across. Well, TCP provides that reliability. So we're going to use that handshake, and we'll go through that here in a minute. And then that's how it handles that reliable, but it is slower, right? Because now we're going and sending a handshake to create that connection. We're going to get packets to come in. They may be out of order. All right, well, now we got to put it all back together. This is a nice little diagram of the different protocols that can run in it. We'll see those a lot on the other ones, but when you start seeing the same protocols across multiple different graphics, that's probably a good tip that those are the ones you should be focusing on. All right, so TCP header, 20 bytes without those options. You want to know source and destination port, sequence and acknowledgement numbers, right? So this is allowing that full duplex and how it's able to put things back together. The flags, we'll go through those here in a second. It just tells what options are in play. And then how much data are we going to allow to send before we actually get an acknowledgement from that receiving destination device that they actually got something. So here's what this would look like What's our source port? Where are we coming from on a source port level? What port are we going to? And we'll talk about the ports and kind of what those common ones are here in a bit. So don't worry about that yet. What's our sequence number? What's our acknowledgement number? So what's the number that this is in the stream of packets? If there's an offset, right? Here's what how your offset works. Here are your flags. You'll make sure you will need to know these, right? You might haven't if it's an ACK, push, reset, send, fin. Those are the big ones. We'll talk through that handshake here. So you want to make sure you understand your flags, and then what options. Same thing here. We're saying here's our segment size. Here's what's coming. The window scale. Are we doing a selective acknowledgement or a timestamp? Yeah, I don't remember seeing anything on congestion notification here. So what you see on this really is kind of the high level of what you need to understand. What is in a TCP header? It's 20 bytes. And what's in it? What is it doing? All right. The ports with this, we're going from a source to a destination. So, there's some well-known port types. There you'll see here, reserved. Anything below 1023 is reserved. That has a list of, like, IANA has a list of well-known ports. We'll go through some of the ones that you'll want to know. And inferior. So typically what happens, especially on a lot of these, you'll start your connection on a source from one of these inferior ports connecting to a well-known port. So, whether it be FTP, SSH, Telnet, whatever, DNS, right? Whatever these well-known ports are, and we'll go through those. HTTP, HTTPS, right? There's the main ones that we are most familiar with, I think, are the ones you'll need to kind of understand. You don't need to memorize all 1023. There's a lot of obscure ones in there as well. But understand, TCP is coming from a source port to a destination port. Typically, that source port is going to be one of those inferior above 1024. And you'll want to make sure you understand that the max number is 65,535 as well. And then reserved ports are below 1023. All right. So sockets is the combination of your TCP and IP, IP address and TCP port on one node. So you're going to be either listening for a connection, you have an established connection. This is kind of showing what that looks like in a Windows environment. So here you can see I've got my my address. It's an internal address on port 139 listening. There's no connection here, right? Versus here, I've got my address with one of those inferior ports connecting to 443, so HTTPS. Okay, so what you'll understand on a socket pair is it's got those five pieces, right? What's my source port, or source IP, source port, destination IP, destination port, and what is the status? Is it listening or established? You also have like the time wait. It's kind of timing out. All right, so you will need to know these flags. Okay, this is where we're going to be setting and letting that receiving destination device understand what's included. What are we looking at here? So is it urgent? Acknowledge. If I send an ACK request or flag, I'm saying from the destination, when you receive this, send me an acknowledgement. Right? Urgent is urgent. Push, meaning just push it to the application. A reset, hey, rebuild this. Let's tear it down and start over. A syn, we're synchronizing. And fin is finishing. We're gracefully finishing this. There are the two new ones added in 2001 for congestion window reduced and explicit congestion notification echo. I don't remember seeing anything about those on the exam, but you might want to know what those for, um, or I'm sorry, what those are for, in terms of like these are TCP flags. All right, you will need to know the TCP handshake. This is very important and absolutely gets tested. So it's 3 ways. We're going to say we're going to do a SYN, SYNAC, and ACK. Okay, so I'm going to, as the client, I choose my initial number, whatever that sequence is, I send it over. The server sends it back in a SYNAC. Both sides acknowledge that they got each side by increasing that sequencing number. Once that is established, once you get that handshake that says, yep, we're good, the ACKs are going for each segment. Okay, so and at the end of this, we're either going to reset it and start over, or we're going to gracefully end it. So what does that look like? Because it's a little hard to maybe visualize if you're not familiar with it. So as a sender, right, I'm going to send my initial SYN with a sequence number. The receiver is going to send it back with their sequence number, and then I'm going to acknowledge and send that back, and then say, okay, we've agreed, we've got this. I want to get a file that's going to request that, and then we send back and forth, right? So hey, I'm sending you 4 TCP segments. I'm going to send back 4 acknowledgements. Once it gets those, I'm going to send 8. Right? So it just continues on once we get past this initial SYN, SYNAC, and ACK. Okay. What you'll see here is what that handshake, what's going on. This is your time to process it, right? So we're at 28 milliseconds. Honestly, this isn't really that important. It's just so you can kind of see and visualize what that looks like. All right. Hopefully that makes sense to everyone. If you're a networking person, or you've done a lot of IT work, this is probably pretty straightforward for you. All right, UDP. Simpler and faster to TCP, right? So there's no handshake, there's no session, there's no reliability. Yeah, send and pray. Very short 8-bit header. Where am I coming from? Where am I going? What's my packet length? And a checksum, right? So you might have some integrity around that UDP header. So UDP layer 4, lossy videos, right? Like streaming audio, streaming video. You'll see it in DNS, right? But what we're saying is we just want fast transmission without really caring a whole lot about that if we lose some packets, right? You wouldn't want maybe packet loss in a banking application or a healthcare application, right? That could definitely be a problem. But if we're streaming video or audio or video, if a couple of them get dropped, not really the end of the day. You're probably not even going to notice that. So that's what you need to know about UDP. Faster, no reliability. It's the cousin to TCP. ICMP, so Internet Control Message Protocol. Layer 3, using to troubleshoot error conditions. Yeah, so typically what you'll see are those echoes, requests, and replies for pinging. And then when you use a trace route. So I'm going to send it out and say, hey, how long does it take to get from point A to point B? And it's going to tell me, right? Or for trace route, how long is it going to take me to get from here, from A to Z, along each step, versus I want to know how long it takes me to go from A to B. All right, so with this, here are your message types. I do not remember being tested on the actual types, but what you'll want to understand is that you've got a type, a code, a checksum. I think ICMP just is going to be, like it says here, really a helper protocol and troubleshooting and reporting error conditions. Now there's attacks against that as well, and we'll talk about that stuff. I don't want to those are the fun ones. All right, So the ICMP ping, named after pinging submarines. So it's an echo request. Hey, I'm going to send it out to a node and wait for that response back. So think about like, the ping from a submarine, right? I'm going to send it out, wait for it to come back. That's going to tell me how far something is, if it's up or down. Now, you can use it to map your target network, right, as an attacker. If you're not turning off pings on your external devices, externally facing, probably should. Why make it easier for people? Again, if it's down or if it's unanswered, right? So if I send out an echo request and nobody replies, doesn't necessarily automatically mean, well, that's down. Just means it's either down or it's being filtered and nobody can get it. It's just going off into a black hole. So trace routes is troubleshooting your how long it takes to go through the network, right? So we talk about like 30 hops, things like that. Well, I need to know where is my problem at. If I'm not able to get to my destination, I can use a trace route to say, okay, I know I can't get to Z. Where along the way is this failing? So what'll happen is you'll send it out. It'll go from, I'm at A, I go to B. It tells me I have a time to live of 30, right? So it's now going to drop. Well, in this case, it has a 1 to a 2. But if I have a 30, every time it goes on a different hop, it's going to drop that count by 1. And then it's going to say, okay, all right, I know here's what each of these different routers are. And then if it fails, that's when you know, well, there's my problem. My break exists at whatever point that it quits responding at. All right, so here, right, this is what it looks like. We've got a time to live of 1, and we might say the time to live is 30, right? So it'll keep adding up. If it can't get to its destination host within its time to live, then it's going to fail. It's just going to die, right? It'll time out. All right. The TCP/IP application layer is combining those top 3 of the OSI model, right? Presentation, session, and application. So all those, how people see it, the session between applications, and how we interact with it, combines all into that application layer in TCP/IP. Yeah, pretty straightforward on that. So what are some of the important things to know about this? So telnet, this is terminal emulation. TCP 23, you will need to know that, right? Make sure you understand that. If you see a port listed here in these slides, it's going to be an important one. They will ask those types of things, what runs on this port. So telnet, no confidentiality. It's all clear text or plain text, right? So including your username and password. If you're using telnet to do anything for management, typically, this would be telnet into your routers or switches to manage them. Please don't use that anymore. Use SSH. All right, but you will need to know telnet is on 23. FTP, file transfer protocol. Same thing as telnet, no confidentiality or integrity. Don't use it to transfer sensitive data, right, over insecure channels. So you'll want to know FTP is on 21 for control connection, right? Where are we sending the connection commands? And then the data connection is on TCP 20, okay? So here, what you'll see is you've got 2 sockets, right? So the client is requesting over on that higher port, inferior port, I need a connection to port 21 over here. And then the server says, okay, we're going to transfer your data from port 20 to 1026 here, right? So we go back. That's how that would work. We're going to have that control and then the data, and you'll use it 2 socket pairs. Okay. So data originates from the server. So what happens is that client is going to say, come in from a high port, random port to the server saying, I need a connection. The server will tell the client, okay, from port 20, connect to me on this port. And then that's how that works. Basically, FTP is typically blocked, right? Because um, or active TCP or FTP, I should say, is blocked because we don't want that server making that connection back. It's filtered. It's a huge risk. Um, yeah. Passive is really only going from the client server as opposed to the server being actively engaged. Again, FTP port 21 for control and then 20 for the data. All right, TFTP, make sure you understand it's trivial. UDP 69. These are all these ports are ones that you should know as soon as you see them, right? This should be second nature to you to be ready for this exam. Really simple way to transfer, right? It's just very minimal, no authentication, no directory structure. We're going to be taking the files, reading them, and writing them from one place. Again, no confidentiality or integrity. So don't want to use this for any sort of sensitive data transfer. SSH, so this should be replacing, securely replacing Telnet, FTP, and then the Unix equivalents of rlog and rshell. There's a whole list of those. So what you need to know for SSH is this is the secure replacement for the those data transfer protocols or management terminal emulation in that case. So this is allowing us to have confidentiality and integrity while securing the authentication. So you can have SFTP or SCP, so secure FTP over SSH or copying it over SSH. You can tunnel other protocols in it. So what you want to know, SSH TCP 22 by default. Yes, you can change these things, know the defaults. And we should not be using SSH version 1 anymore, right? It needs to be SSH version 2. All right, so this is really typically where you would see a lot of the management of network devices at this point should be done via SSH if you're doing command line. All right, make sure you understand these three, SMTP, POP, and IMAP are all mail related. So SMTP is simple mail on server listening on port 25. Make sure you know that, right? This is connectivity between email servers. That's it. POP v3, that's the latest version, and IMAP, our client server, using TCP 110 and 143. So you'll want to know SMTP is server to server, POP and IMAP are client server. POP is 110, IMAP 143. That's it. That's what you'll need to know for the exam. All right, DNS. This is your address book for the internet, right? It's basically a name database. It says, right, FRSecure.com, this is the IP address it lives at. Or, hey, who lives at this IP address? And it'll look it up and tell you. So this will use both TCP and UDP. So typically you'll send out that DNS request. It goes over UDP 53, right? If I'm doing a zone transfer, a lot of times that's more internal type of things, or I'm going to pull it down so I don't have to necessarily look out. That's going to use TCP at that point. Zone transfer needs more reliability and ensuring that connection because we're pulling all the information for the neighborhood or the city, right? If you want to think of it as an address book. So we want to make sure it's correct. If I just want to know, hey, who lives at that address, I just send that over UDP. If I don't get a response, I'll ask again. Make sure you understand authoritative name servers. So I want to know who has the final say for a particular domain. So if I don't know, I'm going to look it up, right? So a recursive will say, think of recursive as like your internal DNS server in a domain, right? You're looking up an internet address, a website, it's not going to be authoritative. It may not know it. It's going to take your request and go and try and resolve it, looking for that authoritative name server. And if you cache, it will cache names previously resolved, right? This is just speeding it up, speeding up looks, making sure, you're not increasing unnecessarily internet traffic, right? If everybody's looking up CNN.com or whatever it is, well, why wouldn't I resolve it locally rather than sending out a request every time? All right. So this is a kind of a really cool diagram that explains it. So here, the client says, hey, I need to know how to get here, right? So I send it to my DNS server that's configured. He says, I don't know who that is. I've never looked it up. I'm going to check another one, right? So it then goes out and says, oh, hey, I do know what that one is. Here's the address. Great. Now I'm going to add it, send it back. Now I know how to get to where I'm going. All right. So here are some examples of either forward DNSs or reverse DNSs. Your top level domains, and then some other top level domains here. Don't remember what G and CC stand for. And then your ARPA for reverse. All right, so there are weaknesses with DNS you'll need to know. It's unreliable using UDP. Remember, it's the send and pray, right? So we don't have any sort of authentication. If we've got a source port and that ID, hey, we could potentially, as an attacker, get in there and send false responses and send you where we want you to go rather than where you should be going. Right? You'll want to know DNS cache poisoning for sure. We're going to trick that caching server into caching that forged response. So what that's going to say is, I'm going to poison their cache and send everybody to the wrong place. And then that will be the case until that record expires. All right, DNSSEC, secure DNS, right? That's really what that comes down to. So the domain name server, security extensions, authentication and integrity to DNS via public key. Doesn't provide confidentiality, right? It's not encrypting it, but it's validating the authenticity and integrity of your response. So this addresses that DNS cache poisoning because I can't forge these requests, right? I need a public key, private key to go there. So I think what you'll need to know for DNSSEC, that this is providing authentication and integrity to your DNS response. There's no confidentiality, right? I can still see what people are looking up, but I can't forge that response and poison the cache. Yeah, it's absolutely been pushed hard. It's still surprising. Very few organizations seem to have this out there. But I know, I can't think of a recent example. I know there were some right around the time we did this class last year that were really high profile, which really pushed for this. And I can't remember what that is off the top of my head now. All right. HTTP, HTTPS, make sure you understand these. HTTP is unencrypted web-based traffic or data. HTTPS is going to be encrypted web-based data, either SSL or TLS. We're going to talk about those later. Make sure you understand HTTP is on 40, HTTPS is on 443. Right? So this is what renders in your web browser. All the information we're sending on over this webinar is over, pretty sure, HTTPS. All right, boot P DHCP, boot P bootstrapping. So diskless workstation. So now I need to know my IP address and then image name, and then goes out and says, hey, I'm here. I need this, and then uses TFTP to download the operating system onto that diskless system. How is it going to operate? DHCP is your dynamic host. This is going to allow assigning temporary IP addresses to systems, managing those things. You can default or configure your systems to receive IP addresses in specific ranges based on segmentation, what DNS servers they need to use, what gateways they need to use, a bunch of that type of information. So DHCP, when a system comes online, it reaches out and says, "Hey, I'm here. What address should I use? What am I going to use? How am I going to communicate? Tell people who I am." DHCP server will reply to that request, say, "Hey, great, your MAC address is it." Or, all right, let me go back. Workstation says, "Here's my MAC address. What IP should I use?" Right? Server says, "Oh, okay, here's your IP." It then adds that to its records and manages that for you. And nicely for this, bootp DHCP is the same ports. So server 67, UDP 67, and clients are using UDP 68. All right, layer 1 networking, network cabling. So we'll need to understand these things. What is EMI, electromagnetic interference? Magnetism. I know we've had this, got some good examples. I know Evan had a good one where every time, like randomly throughout the day, the network would drop in a certain area, and it couldn't figure out what it was, and it did a bunch of troubleshooting, and finally caught it and found that the network cable had been run over the fluorescent lighting in like one of the bathroom. So anytime anybody would go in and turn on the light, you'd have that EMI that was causing network issues. Kind of fun. There's things you need to watch out for when you're doing this. Crosstalk is from one cable to the other. Think of this really back, when you'd have those party lines, right? Or not the party lines. I'm wrong example for that one. You would hear somebody else's conversation on the phone, right? And then attenuation is it's weakening as it travels further. So I can only send that signal X amount of feet or whatever that distance is. As it gets further along, it's going to get weaker and less reliable. So you will want to know these different types. Unshielded twisted pair, what it looks like. It's a set of wires twisted together. It helps reduce magnetism, less susceptible to EMI, but it is still susceptible. All right, you've got, with unshielded twisted pair, you've got different classifications according to their rated speeds. The tighter twist is more dampening. So you can see Cat 6 is for gigabit, then a Cat 3 fast Ethernet. And what does that look like? Here you go. So kind of understand what these different speeds are. Cat 1, that was really your kind of your analog POTS lines. Cat 2, token ring, that's really old. Cat 3 going to 16 meg over 10 base T. And then Cat 4, which you saw again in token ring. But Cat 5 is what most people have seen or heard about. 100 meg or 1 gig if you're using 4 pair, 5E or Cat 6. So here's another nice little chart from firewall.cx. So what you'll want to know is, these are a twisted pair, kind of what the application was, but speeds and distances. It's 100 meters beyond that for the max length. If you're using 10 gig, it drops to 55. Right? So you'll want to make sure you understand kind of what the different UTP categories are, kind of what their rates were, what's their length. They're all twisted pair for this. All right, coax cabling, so satellite cable TV. right? That's really what that's used for. Now, there could be other things, but that's really the important part here for coax is think of your satellite or cable TV service coming in. So you've got that nice copper wire with insulation around it, a copper mesh woven around it, and then you've got outside insulation. So this is going to allow that higher resistance to EMI and higher bandwidth and connectivity compared to a twisted pair. That's what that looks like. The old BNC connector using coax coming in. I don't know if anything uses BNC anymore or not. Fiber optics, light to carry information. So this is where you're going to go past that 50 miles. This is really longer distance, high speed. Those are the two real big benefits, as well as immunity to EMI. So if you see on the exam, what is the cabling that is immune to EMI, or they'll give you a scenario that says, and there's a lot of EMI, what type of cabling should you use? Fiber optic, right? It is more expensive, it's more complex. If it does get broken, it's a real pain to get put back together. But yeah, remember its advantages: speed, distance, immunity to EMI, but it's more expensive and more complex. You'll have two different modes, multi-mode and single mode. Multi-mode is using your multiple paths. So you're going to disperse, right? So think of that as kind of that prism. It's going to go out, spread, come back at the other end, shorter distances. Single mode, it's down one path, right? So it's only one piece of that fiber. You have the wavelength, so I'm going to show you here. Right, so multi-mode, it's going to just send across whatever piece of, across multiple paths. Single mode, just a single one. You can see what that looks like from, you could have a single strand of fiber handle 40 high-speed connections. So, I think that those are really the important parts of fiber. You don't need to know a whole lot around some of those, specifics on how it's managed, things like that. Remember, this is a kind of a product agnostic test, so they're not going to ask specifics around Cisco or Juniper or whatever the technology is. All right, and then Ethernet is your most common framework or technology. So we're going to send the data in frames. We'll talk about these different topologies, but you had a bus or a star where it's connected, token ring. It's a ring. Each thing goes around, and we will talk about those, I believe, in the next class. Ethernet happens layer 1, layer 2 issues for physical medium, so the actual cabling or the frames over the into the NICs, and it's one channel, right? Remember, broadband, TV, baseband, one channel. It's just one thing coming across. This is a kind of a nice little chart I found updated for this. So just kind of understand high level kind of what the different types are. What cable type is it using? Kind of some max distances. You don't need to know really a whole lot of detail beyond that. Just understanding, what are our Ethernet types? What kind of type? What do they use? What are some bandwidths? All right. So with Ethernet, when you have that, you can have those collisions on your network, right? It happens. So you'll have carrier sense multiple access addresses that. So with the collision detection, it's going to sit and listen and say, is anybody talking? No. Okay, I'm going to send out my information. And while I'm transmitting that, I'm going to keep listening. I'm keep monitoring. If I start getting more current data that somebody else might be sending, all right, I'm either going to say, no, every detection wired, I can send and receive at the same time. If I can't do that, I'm going to do collision avoidance on wireless. So on that, I need to send out and get an acknowledgement from the receiving device before I can send anything. If I don't get that acknowledgement, the avoidance piece that goes, oh, well, there must have been a problem. I got to wait again and try again. I can't send until I know that there's no collision in place. ArcNet and Token Ring are really, really old. Pass network via tokens. Whoever has that token to either read or write gets to do what they get to do, either the read or the write. Right? There's no collisions because only the person in possession of that token can do anything. Waiting for that. So yeah, 2.5 meg, a star topology. Last version ran 16 meg physical star logical ring. My last professional experience with Token Ring would have been in 2001, 2002, converting some or businesses off of it. What you'll need to know for this is really old stuff. Yeah, I'm sure there's still some out there somewhere, but Token Ring, ArcNet, pass traffic via the token, and only the device or that node that has the token that allows the read-write. FDDI or FDDI, Fiber Distributed Data Interface Legacy, right? So you got 2 rings, primary, secondary, counter. Second was being used for the fault tolerance. So token bus, but it's similar, right? It's just using token passing. So what you'll need to know for this is that it had 2 rings, primary, secondary, counter rotating, fault tolerance, and uses a token bus. Really don't need a whole lot of knowledge, deep knowledge on how that works. So the bus topology, it's in a string, right? So everybody's in the bus. It's going down its path. It's following its route. So as I get it, right? So if I'm node C or node B, node A sends the traffic. I look at it, say, nope, that's not for me. I pass it to the next guy, right? So the problem is if one cable breaks, we now potentially lost that connectivity, right? If it's going to node C and it breaks between B and C or A and B, we're down. Doesn't help us out at all. Tree, hierarchical, man, it's getting tough to talk. Yeah, it looks like a tree here, right? So you've got a root node, the one, mainframe, that would then talk to others and pass that traffic down. It still goes, it's not often used. I don't know if I've seen it anywhere for the physical topology. Ring. So this logical ring, physical star, what you'll need to know is that it connects them in a ring. That's exactly what happens. It can go either direction on that ring. If it breaks at one point, it does cause interruption. It could potentially make it longer. Star topology. So this is the most dominant one for LANs. Ethernet is what it's using. So you've got a central hub or switch that goes through and all the traffic goes through, right? So we don't have a single, like the bus, if one thing, one cable dies, everything goes down. If a cable dies, it's just that node or segment that goes down. All right. So here is what you'll want to make sure you remember. What is the difference between physical and logical topologies, right? So if you see the word ring on the exam, make sure if is it physical, logical, or both. They will give you the hints on there to make sure that you understand and are able to get the right answer. But you want to make sure that you pay attention on the exam what the context is. All right, mesh mesh topology, again physical, connecting those nodes to each other. You have a full and partial. This is where you see the high availability clusters, right? So in this is your full. Doesn't matter. We could lose any one connection and still maintain full connectivity, right? We've got double redundancy in place. Here, we could potentially lose, some connectivity and cause some issues. So, um, in this case, full, everything's connected to each other, right? And then here, partial, these three devices are all fully connected, and then these two do not have that additional connection across. So full mesh, everybody's talking, everybody has a connection. Partial is exactly that, just some subset of devices have a connection. All right, and with that, oh, come on, hey, there we go. Probably a little bit easier for everybody tonight, I hope. Again, a lot of technical information, but if you notice, it doesn't go super deep, right? And there's no specific technologies. We don't have to worry about, what Cisco or Juniper or whoever is doing. We just need to know the concepts for it. So Wednesday, we're going to finish off this chapter, this domain. Make sure you have questions. I'm going to leave the chat up here as people continue. But with that, I appreciate everybody staying with us, and hopefully a little bit more fun than the security model from last time. So thank you, everyone.